Hi again, Calc AB, welcome. Today we're talking about a new topic, a new application of derivatives, or a use for derivatives anyway, and it's something called differentials, and it goes by a couple of names actually, or different applications. You may call it something a little bit different, but in the end, ultimately what we're talking about is something called differentials. And what this is going to focus in on a lot is about a tangent line approximation to a graph. When we did this earlier, we wrote the tangent line equation for some functions at a specific point. And what differentials does is it takes advantage of the fact that linear equations are a lot easier than some of the more complex functions that we're going to be dealing with. And this is kind of harkening back to the days of Newton and Leibniz when they were first getting started. They didn't have graphing calculators. They didn't have computers. They didn't even have a slide rule. And if you don't know what a slide rule is, yeah, you should Google it. That's what they had to use back in the day. If you've ever seen the movie Apollo 13, you'll see once they realize, they get the message, Houston, we have a problem. And they start doing calculations. You'll see all these guys whip out these things that looks like a ruler, only there's several scales on it. And they've got this thing that slides up and down. It's got this thing called a hairline on it. And that's a slide rule. And that's how they had to do computations back, as recently as the 1960s, because the first, numeric calculators and computers and stuff didn't really exist until this 1960s. And so, Newton and Leibniz didn't have that. And so they relied pretty heavily on their new invention, calculus, to come up with linear approximations to functions so that they didn't have to work with the curvy, polynomial, trig, whatever it was that they were dealing with. So that's where we're going to start. And we're going to take a look at this. I've got a couple of examples planned out for us. And then hopefully when you get to class, either with me or with Ms. Hoagie, if you still have some questions about what differentials are used for or how they work, we can answer them for you. So let's just dive right into it here. I've got my first example. What I'm going to do here is first define the differentials. So if I say my function, if I say, okay, let's let y equals f of x. So just y is some function of x. And we're going to say, let that be a differentiable function. All right. I always writing out the word. I always like writing out differentiable because it's got so many letters. It makes me feel smart. Let me a differentiable function. Then the differential of x which we denote dx, is any non-real zero number. Non-zero real number. The differential for y we'll denote that dy is, okay, now I want you to imagine taking the derivative of our function here, okay? So we would take dy over dx, right? Using our Leibniz notation, and using our Newtonian notation on the right-hand side, we'd say that's f prime of x, yeah? Well, here's what we're gonna do. We're gonna move the dx to the right side of the equation, like so. And we're going to show that dy, the differential of y, is equal to f prime of x times dx. And so it may feel a little weird right there, like, whoa, I didn't know dy and dx were actually separate things. I thought that was just Leibniz notation. Surprise, yeah, they're actually different things. And they're called the differentials, the differential in y and the differential in x. Back when we first introduced this idea of a derivative, we talked about slope, right? We talked about how that's the slope of the line. As you move the 2 points together, closer and closer on the curve, we get the slope of that tangent line. So it's kind of like delta y over delta x. There were two different things. Well, that's what's happening now. we are moving those two lines closer and closer together, or the 2 points closer and closer together. We're just now going to separate out the dy from the dx. This becomes a much more important idea later for us in chapter 5. And so it's kind of good to introduce it now, show you kind of some things we can do with it. And then later on, chapter 5, we'll really put this to a lot of use. So there's a few things along the way here. We kind of sprinkle them in early on, and then they kind of come back around later on. And this is one of those ideas. So let's start off with my example here. I have f of x is 1 plus sine of x. And so what I'd like to do is just say, well, what is my differential going to look like here? And what I want you to see is that if I find the tangent line equation for this function here, okay, so let's find the tangent line equation, right? What do we, let's find the tangent line at the point 0, 1. Okay. Obviously, I put 0 in for sine, right? We get 0 plus 1 is that. So what's my tangent line equation look like? Well, to do that, right, we need two things. We need a slope and we need a point. We've got the point, so now we just need the slope, which we can find from our derivative here. What is the derivative of 1? Well, that's constant, so it just derives away. And so we're left with the derivative of sine, which of course is cosine. And so now at 0, we get a slope of 1. I gave you, kind of an easy point, right? That's the y-intercept. So we can actually write the tangent line equation here. If I use a y equals mx plus b, right? You just get y equals x plus 1. Okay, and so my differential, okay, dy, all right, comes from the slope in here, right, where we have multiplying by x. And what I want to show you is that the tangent line, y equals x plus 1, and the original function, f of x equals 1 plus sine x, the reason we're interested in the differential here, okay, is that as we stay close to the point of tangency, you're going to see that the function itself is not that much different than its tangent line. And so I have got a graph for us over here on Desmos, and you'll see a red sine wave. Okay, the red curve, there's the sine wave. And I've taken, oh boy, nice. That's why I teach math, right? I've taken the liberty of graphing our tangent line at the same time. And what I want to call your attention to here, guys, is notice at the point of tangency, there's no difference between the curve itself and the blue line. And even as we move out, even as far as, maybe here to here, there's really not that much difference between the blue line and the red curve. If I zoom in here, I think I can do that with my, let me just pinch zoom this. I just, hit the plus. Oh, I'm in annotate mode. That's the problem. There we go. If I zoom in far enough, move my point of tangency there. What you see is that there's really no difference, right? There's my point of tangency. The blue line and the red curve are indistinguishable. Now we're pretty close in, right? I mean, like if you look down here, you can see, oops, I didn't mean to do that. You can see down here, I'm within, 0.1 of the point of tangency, but that's the whole point. As long as we stick close to the point of tangency, there's really, if I found my differential or a delta x, the change in y on the curve is the same or really close as the same as the dx and the dy, which are the slope of the tangent line, right? Okay, if I were to go over 0.05 on the graph, 1 plus sine of x, okay, and then see what my corresponding change in my y coordinate is, that's very similar to the slope, rise and run, of the tangent line. And that's the whole point for differentials. As long as we're sticking close, as long as delta x or dx is pretty small, you can use the tangent line instead of using the curve. Okay. And that was the whole point behind what Newton and Leibniz were trying to do, because they were, again, living in a world without any sort of calculation machine, whether it be a slide rule or a calculator or even a computer. So that's what they did. So let's take a look at where we go. Back to our examples here. So the whole point is the slope that's in our linear equation. Okay, when we make our linear equation here down here, okay, this slope, dy over dx, is a really good way to approximate a vertical change in f of x for any given horizontal distance that we want to go over, as long as we stay pretty close to our point of tangency. That's kind of key in this one. All right. Here's another example of where we might use this idea. Okay, the error propagation. As you know, when you measure something, if you're in science class at all, you've been talking about sig figs, right? And in math class, we don't usually talk about sig figs. We don't usually worry about sig figs a whole lot. But they are important because depending on how accurately you can measure something, okay, that will have an impact on the number of sig figs that you could use. And even more so when we start using those measured values to do computations, the amount of accuracy in the measurement propagates an error into whatever computation we are going to do. And so my example here is for a sphere. So, if I have a sphere, I'll do my best to make this look 3D here. And I measure the radius of my sphere to be 0.7 inches. Okay. And then I use that measure to compute the volume of that sphere. Okay. I would get, let's see here, volume of the sphere is 4/3 pi r cubed. Okay. So 4/3 times pi times 0.7 cubed. And I would get a volume of 1.43676 inches cubed. 4/3 pi r cubed. Yes. Okay. Sounds good, right? Except the tool that I use to measure the 0.7 inches isn't 100% precise. They never are. Okay. There's always going to be a little bit of error there. If you look in your book on page 230, there's a nice picture of something called a micrometer. Now, if we were live in class, I would get out my micrometer, and I do have one. And I could show you that the micrometer, while very accurate, much more accurate than, say, my ruler that says, it's a say no to drugs ruler. Fantastic. If I had my ruler, it's not nearly as accurate as, say, a micrometer. But that doesn't mean that the 0.7 inches is actually right on the money. And it says right here that my micrometer is accurate to 0.01 inches. Well, what we could do is we could use a differential to say, well, here's how accurate we think our volume measure is going to be, because we can find dV in terms of dr, where dr is the differential in the radius. So come back here, 4/3 pi, those are all constants. And what's the derivative of r cubed? Well, it's 3r squared. Okay. Now remember, there's a dr. So now We'll do a little algebra here and clean that up. We get 4 pi r squared dr. So the propagated error can be approximated using a differential. And let's go ahead and plug everything in. 4 pi 0.7 squared. The error in the measurement is 0.01. So let me come back to my calculator, and I've got 4 times pi times 0.7 squared times 0.01. And I show that the dV, the differential in volume, is 0.061575 cubic inches. So yes, if my measurement is exactly right, 0.7, then the volume of the sphere is 1.43676 cubic inches. However, knowing that the accuracy of the tool I'm using is limited to 0.01 inches, my volume could be off by as much as 0.061575 cubic inches. That is my estimate for the propagated error in the volume of the sphere. How about that? It's using the linear equation, that tangent line to the volume equation, 4/3 pi r cubed, to approximate, okay, if I go over horizontally 0.01 inches, so instead of 7, it's 7.01, how much vertical change do I expect to see? Oh, I expect to see about 0.061575. Now, that's not exactly right. It is an approximation. Okay, I do want to be clear about that, because we're approximating with the tangent line, like we saw with the sine wave. Okay, you're going to have some error here, right? Okay, yeah, I can certainly graph what. Oops, y equals 4/3. Oops. Pi x cubed. There's my volume, right? And I can graph, oh, where's that? There we are. All right. And where are we? Oh, I'm still zoomed out. There we go. And you can see, let me get my annotating tool here. Here's 0.5, 0.6, 0.7 right here. And here's that volume that we said we were going to get. Okay. But if I were to go over just a little bit, 0.01, you can see that there would be an increase in volume. But what I'm saying is, let's use the tangent line here rather than this cubic polynomial to figure that out. And that's what differentials aim to do. So, all right. Let's go back to the whiteboard here. There we go. All right, so there's a nice application of differentials, error propagation. Another application of differentials that you will run into, this one comes from economics. Now, in economics, they don't call them differentials. They call them marginals. Okay, so like we'll talk about marginal profit or marginal cost or whatever. And typically, what they're trying to do is, in an economics, a microeconomic situation, you're trying to maximize profit, right? So trying to figure out where that maximum profit is or where the minimum costs are going to be. And so if you think about it in terms of a differential then, and what that means, well, how do you know when you're at the maximum if you're looking at a differential? Well, what would the slope of the tangent line be at that point? Okay, at a maximum. be 0, right? That's where the critical numbers are. So what they'll oftentimes say is something like this. So completely made this up, totally made this up on my own here. But it says, how many sets of AirPods should Apple produce to have a marginal profit of 0, given the profit function below? So they're talking about, okay, the marginal profit, the profit from adding one more set of AirPods is 0. What they're really saying is, okay, marginal profit means the tangent line is flat. So all you really have to do for this one is to find where the slope of the tangent line is going to be 0. In other words, if this is y, is our function p of x, where does this happen? Where does dy equal 0? Okay. Given that delta x and dx is going to be one more unit. Okay, that's how the economics application of this is usually phrased. So marginal profit is 0. That means if I add one more unit, if I sell one more set of AirPods, it doesn't do me any good. I've maxed my profit out. Well, so let's just find the derivative with respect to x of our profit function. Okay, well, 1/16 x squared, bring down the 2, subtract 1 from the power, minus 125 over 2. Okay, and then this guy here, this is the constant, right? It derives away. So here we go. Set this guy equal to 0. And you're going to get x over 8 equaling 125 over 2. Or 2x equals 125, so times 8. And so x should be, oh gosh, I forgot a 0. Sorry. So let's see, profit is in millions of dollars and x is in thousands of sets. So we should sell 500,000 sets of AirPods to maximize our profit. Okay, in other words, make the differential in profit equal to 0. And I should add that the dx, because we're setting the whole thing equal to 0, it doesn't matter that dx is 1. So the derivative or the differential for p of x is really 1/8 x minus 125 over 2 dx. But the idea is to figure out where to make this 0. Well, dx can't be 0. It's always going to be one more unit. That's how it works in economics. And so we just set this equal to 0 and show that, well, if x is 500, this is 0 times whatever dx is. So it doesn't matter if you sell 1 more, 10 more, half of an AirPod set more, you're always going to get a differential for the profit to be 0. So we know we're at a maximum. So that's a nice application from econ. I know we tend to focus a lot on engineering here in calculus, but there are applications outside of engineering for a lot of this stuff. So I like to bring in some economics there for you. My last example here is just another kind of simple one. This is actually an example from the book. I think it's on page, what is this, 232. Use differentials to approximate the square root of 16.5. Okay, well, so what I want you to think about is, if this was our equation, okay, what would the differential look like? Well, we'd bring down the power, subtract 1 from the power. Okay. And 16.5, do we know a square root close to 16.5? Yes, we do. What about if x was 16 and dx was, we would go over 0.5. So what is dy at that point? Well, we have 1 over 2 root 16. Okay. Well, 1 over 2 root 16, that's 8 times 0.5, 1/16. So the change in y, if you go from 16 to 16.5, is 1/16. So the square root of 16.5 is approximately 4 and 1/16. Now let's see here. The actual square, I'm just looking for the actual square root, but I don't see it here. So if I actually use my calculator, I'll just use my calculator because I didn't see, oh, I think I just saw it there, but that's all right. Is, excuse me, 4.0602, okay, and 4 and 1/16 is 4.0625. Look how close they are. Yeah. So we can use that differential to approximate that, and it is really close, right? So there you have it. Differentials, much much nicer than dealing with actual nasty functions. Obviously with us, what did I do? I just typed in a calculator. So yes, that's very straightforward. But back in Newton and Leibniz's time, they were not so lucky. They didn't have a TI Inspire, TI 84, or 89, or Desmos, or whatever we were using, right? So they relied pretty heavily on differentials and using those approximations, those tangent lines around the points of tangent. All right, guys, that's it for differentials. Hopefully those applications and examples made some sense. If not, well, then Miss Hoagie will be there to clear it up for you on Monday, and I'll be back on Tuesday for my kids to go through some questions if you have any more of those. So, all right, thanks for watching, guys. Have a great weekend, and I'll see you on Tuesday for my